So before this talk, I was actually going through the previous reading sessions, and some of them were really math intensive. But I'm trying to keep my talk as exact as possible, giving more of an intuition behind it and straying away a little from the math because so that anyone can understand it. That's the motivation. And I've seen that the average length of the talk is going around 30 to 40 minutes, but I think the ImageBind paper by itself is a quite intuitive and simple paper. So I'm not going to stretch long. I'll just go to the point, and I think I'll just try and keep the talk as succinct as possible. And then maybe post the talk if there's something we can discuss. Let's discuss, right? So can you all confirm if you can see the slide?
Yeah.
All right, cool. So before we start, maybe a small introduction about myself, just for knowing at what state I'm at in terms of knowledge, so that there might be some cases where I'm not able to answer your questions pertaining to this paper. So hi guys, I'm Sridhar. I'm currently in my final year and I'm pursuing BTech in AI. So yeah, so as I said, I'll just repeat myself that at some points where you might have some questions with the paper, I might not know the answers. And that's when I'll take a day or two and then get back to you, right? So ImageBind, one embedding space to bind them all. So before I start my talk, I just want to ask you all, did anyone read this paper before? Does anyone have some understanding of it?
Yeah, I kind of gone through it on
Okay.
ImageBind. It's kind of like a self-supervised methodology on multiple
Yeah, yeah,
modalities.
yeah,
So
yeah.
I don't want to spoil anyone. So
Exactly,
I'll
exactly.
just
That's the reason why I asked. Because I'm going to ask one or two easy questions to give it interactive so that just for people to answer. So if you've already read the
yeah.
paper,
So
don't
I'll
give
be
anyone
back
a problem.
just
Yeah,
watching.
yeah, cool, cool. So I mean, so yeah, so that's now that that's out of the air. But when someone says image bind, can I just know what pops up to maybe Yasmin your head or Mayank your head? I'm assuming you didn't read the paper. When I say the word image bind, what do you think about?
Oh, I have read the paper. I just
Okay, you
yeah.
already read it.
Yeah.
Okay, oh shit. Maybe someone who's not read the paper. What does come to your head when you say image bind? Okay. Uh, Seems like a tough crowd. But basically, what I'm trying to say is you're trying to bind everything with images, right? So that's the idea that comes to your head when someone says image bind. Now, before I get into the nitty-gritties of the paper itself, I just wanted to give a small recap on what are vector embeddings, where basically, if you look at all these large language models, transformers, RNNs, CNNs, all these deep learning models, they don't understand the world like we do, where now I'm talking to you and you're able to understand what I'm trying to say. But when it comes to these machines, what they understand are numbers, right? So the text or the images that we have need to be converted into numbers. So these numbers are known as vectors, okay, where essentially you can define how you want it to be, but the general understanding is that each image can be converted into its own vector, where a vector is a single column multi-row, like a K cross and matrix, right? And these numbers are passed to your model so that the model can understand whatever you're seeing or you're typing, right? So there are multiple ways to do these embeddings. For text embeddings, you had something like skipgram and cbow. I'm not going to get into the details of it, but post the talk, maybe we can talk about them if that's something you want to get into. And then for images, you have something like encoders, image encoders, or you can use something like a basic CNN to get a basic embedding of them. So now that you know what embeddings are, and that's how deep learning models or machine learning models in general understand them, let's try and understand where these embeddings are used for, right? So, for example, I'm going to take two use cases where these embeddings are being used in the industry to do certain activities, right? So something that is very popular right now with the LLM bandwagon is RAG, which is retrieval augmented generation. So now I don't want to scare anyone or anything, but I'm going to be a little abstract and then explain what's happening here. So essentially what's happening here is you're taking all your text and you're converting it into embeddings, right? And you're storing all these embeddings in a database, right? And now when you give your new query, that by itself would again be converted into another embedding. And then given this text embedding and the database embedding, you apply cosine similarity. So cosine similarity is nothing but if you give it, let's say, two numbers or two vectors, it tries and tells us how close the two vectors are to each other, right? So that should give you a sense of what cosine similarity is. And once you know what your question vector is similar to in the vector database, you get those embeddings and then you give it to the decoder of the LLM, and then that converts that embedding knowledge into English. So when you import, let's say, or upload a document of a research paper, and then you ask ChatGPT, hey, what's this in the paper? The behind the scene is some to some extent this, right? That's one application of vector embedding. And another application is if you know the clip model, where essentially what they try to do is they try to take. So the reason I'm explaining clip model here is because I'm trying to foreshadow something for the ImageBind paper, right? So if you look at the clip model, what they tried to do is they essentially took image and text pairs, okay, vectors, and then they converted them into vectors or embeddings, right? And when I say pairs, I mean like, so they had a dog image, as you can see, and then they had a description of the dog, a text of the dog, right? And then they created multiple XY pairs like this, right? And then what they did is they tried to train a model where, let's say, it was more like a contrastive based law. Now, when I say a contrastive based law, so what I mean is, I'll come to the last function used in ImageBind, but just to give a precursor to what a contrastive based loss is, what that basically does is, let's say if I give you 10 images of cat and 10 images of dog, and then I create pairs of cats, cat one, cat two, and then dog one and cat two. Like I create these sets of pairs, and then I try and train a model. The loss function over there, what it tries to do is it tries to understand the similarities of features of cats, right? And the similarities in features of dogs, and tries to contrast the differences between a cat and a dog. So if I put a cat and a dog to the model, it'll understand by converting into vectors and then post training, understand that hey, these vectors are really dissimilar. And so yeah, the other one is not a dog, right? For the cat and the dog example. So over here, what they tried to do was they took these dog or other images and the corresponding text with it, and then they trained with contrast loss a model, right? So what am I getting out of it? You explain this jargon. What's the use case? So the use case behind this was tomorrow when I type something, I'm able to get relevant images for it because I've trained a model for text and image, right? So now if I have to, let's say, extrapolate this concept from here and go to other modalities or other senses, for example, audio, or for example, video, or for example, even depth images or thermal images, uh, 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 to some an intuitive sense that you can grasp from this is, hey, now I've done text and image. Why don't I do audio and let's say text, right? Same concept. So after I do this, later on when I say type something, I get audio pertaining to what I'm asking. So let's say I type a gunshot, I get an audio of gunshot, right? So now you could generate that audio, or you could search it from a vector database. That's on you. That's how you train your model. But now when I say, hey, I want to combine, let's say, an image, okay, and audio and text. So let's say now if I give an uh, text prompt, like I say, a gun being fired in a let's say in a desert field, Now I want it to generate an image of the gun being fired in that desert field, and I also want the sound of the gun, right? So in that case, if we go by the concept that's being followed here, where you're having pairs, you need to have an image, right, of the gun in the desert. You need to have audio for that, and you need to also have the text for that, right? So now, if I want to expand it into more modality, getting these complex pairs would sort of be hard, or it would be laborious, right? So what the guys at ImageBind or at Meta did is they said, hey, uh, instead of having to collect all of these embeddings, uh, why not use the image as a middle layer for these translations? Now, I will explain in the next few slides what I mean by that. But yeah, so a major obstacle, which I wrote in the slide, which I've taken verbatim from the paper, a major obstacle in learning a true joint embedding space is the absence of large quantities of multimodal data where all modalities are present together. So image, audio, text, and other modalities, whatever you want to expand into, present together for that particular example, right? So yeah, so that is, I've explained audio depth. IMU is initial measurement unit. I'll come to what that means in a bit. Okay, for creating a joint embedding space, right? So now the intuition behind the ImageBind paper, I'd like to explain it using this image, right? So now when I show you this image, you see a beach, right? And if I tell you to, let's say, close your eyes and imagine that you're at the beach, you'll be able to listen to the audio, right? You'll be able to feel the beach, uh, and other modalities of you experiencing yourself to be in the beach, right? So I for myself took this as the intuition behind the ImageBind paper, where as humans, when we're able to do this, um, why not try this concept out for multimodality based let's say indexing or generation for large language models or any other deep learning model, right? So the concept that they used over here, if you see, is they use the image embeddings as the middle layer for communication between other modalities. So what I mean by that is, tomorrow, let's say if you type, I want a gunshot audio, you don't specifically need to have a gunshot audio text. Sorry, a gunshot text and the gunshot audio, both of them put together as samples to, let's say, train your model and then ask it questions like this, right? Well, what you can have on the other hand is just, let's say, text of a gunshot and then an image of a gun being shot, and then the audio of gunshot, and then the let's say spectrogram of the audio of the gunshot, right? And then you train your model, which I'll come to in a bit. You train your embedding space, and then you could traverse between the text to the audio without having to being specifically trained on audio and text, where you're using the image as the intermediate binding layer. So, for example, let's say you want to translate something from Telugu, where I'm from Hyderabad, Telugu to English, right? But then the Telugu guy doesn't know English properly. Okay, so what he could do is he could go to his Hindi friend who knows English very well and Telugu very well. He can tell the Hindi guy, "Hey, I want to say this in Telugu to him," and then the Hindi guy can understand what the Telugu guy is trying to say, and the Hindi guy can convert it into English, right? So that way, the communication between Telugu to English is happening indirectly. So if you look at the image, where if you have f of x, a function, and you have h of x, another function, if you want to map, let's say, a value from f of x to h of x, and you don't have a direct mapping for it, in this case, you don't have direct data for it, you can do an intermediate mapping where you map from f of x to g of x, and then from g of x to h of x. Okay, so that's the main concept behind ImageBind, right? So now you could ask me, hey, all this is fine. So practically speaking, how exactly did they do this, right? So when they created this data set, you are able to find text and image pairs very comfortably, right? Now, how did they bind audio and image, right? How did they bind depth and image, right? How did they bind other modalities of image, right? So from what I understood from the paper, for audio, what they did is, so when you take these audio, let's say wave amplitude functions, you can plot these as images called spectrograms, right? And for the depth and the thermal aspects of it, from what I understood, they took these as images, thermal images and images, and then they were just trying to map depth and let's say thermal or other kinds of modalities with image, right? So this is how they tried to do this indirect mapping from, let's say, audio to text, or let's say I don't know, let's say depth to audio. Okay, so how did they do this, right? So this is where I said I would come back to contrastive learning and explain exactly what's happening there, right? So the last function being used in the paper is called info uh, NCE, if I'm not wrong. Okay, so basically what's happening here is, let me break this mathematical formula to you, right? So Q and K are embeddings, right? So vector embeddings of any I to M pair. So if I get example where you have I comma M, where M pertains to any other modality and I pertains to images, uh, these samples are then encoded into embeddings, right? After they're encoded into embeddings, you are trying to let's say close the distance between them if they are two supposed to be similar. Let's say a text that says dog and then the image of dog, you're closing the gap between them, those two vectors, or you're trying to increase the gap between them if they are not same, if they are negative pairs and positive pairs. Okay, that's what you say. So how exactly are you trying to close the gap between them, right? So I've said it in English, right? But how is that happening math-wise? So if you look at the laws, now generally, whenever you're training models, you're trying to minimize the loss. Okay, so in this L I comma M loss, you're trying to minimize this minus log value present, right? This huge value present. So if I'm trying to minimize my minus log value, I'm trying to increase the value present inside the log, because from what I understand, minus log 10 would be lower than minus log 5, right? So when I'm trying to minimize this log, minimize this log, you have a numerator and denominator, right, for this fraction. Now, if I tell you, I give you a fraction for numerator and denominator, and I tell you I want you to increase this value, what would you do? You try and increase your numerator, right? Or you could try and decrease your denominator. Yeah, I guess so. But let's just go with increasing your numerator, right? So now when I'm trying to increase my numerator, I'm trying to increase my e to the power qi transpose ki by, let's say, tau or t, whatever you want to call it, value, right? So when I'm trying to increase that value, I'm trying to increase the qi ki value, right? Now, qi transpose ki, given that these two are vector embeddings of same size, that basically is the dot product between both of them. So what we're trying to say is we're trying to increase the, uh, let's say, the similarity between those two given vectors in the joint embedding space. Now that's how I understood this loss function. Maybe post my explanation. If I did go wrong or if there's something that can be added, please add into it. Right? Now, all right, you explained this concept of image bind. You've shown me some math. So what does this change? Right? So that's where let's look at some applications of ImageBind, right? I see what the whole magic or the point of this entire paper is, right? So I just wanted to confirm you're still able to see my screen, right?
Yeah.
All right, cool. So let's say you have image and audio, right? Which, so this is the ImageBind's demo website that's given in the paper, and it's in the slide. I'll just move back to the slide after the demo. So basically, let's say you have an image, right? And you want to get or generate audio that pertains to this image. Okay, but you don't have let's say pairs of this uh, the dog image and the audio of it, right? You don't have much data for it. So what maybe you could do is you could train your text and dog, right? You would have multiple. You could say this is give a description of the dog, maybe German Shepherd or whatever, and then give images of that. And then you could also have the dog barking sound, and then generate spectrograms of it, which are images, and then try and do contrastive learning on that, and thereby you could do an image to or a text to audio or even a image to audio kind of scene. So I'll just show you a couple of different cross modality retrievals or generations that are possible to this demo, and then I think I can wrap up the talk after that, right? So let's say you have a dog here. Now you want its audio. So instead of having to specifically train with dog audio, with just image being the intermediate layer, this is the audio that has been generated. So are you guys able to listen to the sound? Can you guys hear this?
No.
Is that odd? No, right? No. All right. Give me 1 second. I'll try and figure that out. And I'll show you an example that I have here. Yeah, yeah. Are you guys able to listen to the sound? Are you guys able to listen to the sound?
No, not yet. Can you just play that again?
Yeah, yeah. Yeah.
No, no, not yet.
No?
I
Okay.
can't hear.
Let's just move to another example. Yeah. So if you look, all right. So so what you did over here is once you do your image binding where you try and traverse through cross modalities without having to train through them, there are a couple of things that you can do. So this is one of the many things that can be done, and I'm going to show you in the demo. Okay. So let's say if I give it the sound of a dog barking, and then I give it an image of the ocean, and then I say, hey, what can you combine these two? The model will understand and it will generate an image or retrieve an image of a dog in the ocean, right? So it understands from the audio that it's a dog, it converts it into a vector. It understands the image, converts it into a vector, and tries to search for an image in its database where both of these vectors are put together really close. In this case, that would mean a dog in the ocean, right? Uh, apart from this, apart from this retrieval, you could take this concept, you could take this embedding, and in the paper they explain it more clearly. So I would just say read the paper for more information as to how using this embedding concept you can even overlay it on diffusion models and other trained models between two modalities. With these embeddings, you can replace the embeddings with these embeddings and generate something like this. So let's say if I give it the audio of rain, it can generate the image which has rain in it. If I give it audio of a dog, it can generate an image of the dog. If I give it the audio of an engine, it can generate, let's say, in this case, it's say the ship that has or a boat that has a engine, right? So those are a few examples that I wanted to show. So the and so that you could at least get some idea as to what the benefits are of doing this image bind therapy, right? So this I've lifted off from the paper where you can see that they can do one that is embedding space arithmetic, that is combining two modalities and getting an output for you. Another is they could do cross modality retrieval, which I just showed, where you could have just audio and then the image of the dog you could retrieve from your database, right? And you can also do generation. So these are basically the three main things that they try to achieve using the image bind paper, right? So yeah, I hope you guys got some idea of image bind. I have tried to explain it in, let's say, 20-30 minutes. I didn't go into the depths of it because my whole aim was for you guys to read the paper after the talk. Now I think we can just open the discussion to the floor. I'll just stop sharing the screen.
So guys, like kindly ask what and all like doubts you got from this session to Mr. Streaker. So if there is no doubt, like I'll kind of like say the continuing point of like how this image bind is got evolved. So
Yeah, sure. Please do.
so I think like no one is there, but I'll just give you an intuition on what could be the next from the image bind paper. So on the image bind is like what the authors have initially told us. Uh, these like within images as well as on audio, you kind of like make indirect distribution between on videos too. Like yeah, so with the text and video could be like directly related, but with the text and with the image, it could be indirectly related to the audio as well as it applies to video. So those dotted lines in that image bind is like it's like not explicitly intended to align, but the way it is like if you take a video and an audio, the frames of images and an audio makes a video, right? So that's emergent alignment. That's what the entire paper is based on. So with the explicit alignment, what I have, how could I get into some kind of like emergent alignment? So thus making the process really easy. So with that, what they did on a blip 2 is like they explicitly took this only modality like image to text generation, text modality. So after this, like on after doing this representation learning, each could be used as each thing like this could be used as for some kind of like image encoder for a diffusion model or something, just like lip, and this could be used as for cross attention based text based generation diffusion model. So like the that's what's like advantage of this thing, representation learning. So you kind of like explicitly learn the representations. So yeah, so if you look into this, what I did is like they kind of like made it into a single transformer block. If you look into this thing, so if there is like no masking between tokens, there is like full alignment between like full image and text is considered. And if you just want to take only one alignment, you just mask out here and here on the test. And if you want to mask out only on image, like give the entire image and make it causal attention, like the vanilla attention, vanilla decoder only attention, that's causal attention. So to do that, shoot, I'm stuttering. So I'll just turn on my video, so it will be like really easy. So I could like draw it by left hand. Into like causal attention, like the next word and next word, what it is. So you could also do this here. So it kind of like came into an idea of ImageBind, and they kind of like explicitly mentioned doing this thing. So yeah, so there is also this thing like people who are like looking into this image bind and everything, you may ask like, what's really the use of like uh, doing this much like compute to uh, align these two networks. So if you are looking into working on multimodality, like this will be like really helpful. As well as if you are learning multimodality, you will also be learning unimodal distributions really well. So that's the any point. Thank you. I kind of like hijacked it. I'm sorry.
No, no, that's very nice actually. In fact, Madhava, share this paper with me. I would like to read it post this session.
Yeah, sure. On the AI4Bharat Discord, I'll share it.
Yes, yes.
Just a quick comment. Shrikar, you should have gotten into the nitty-gritty of the paper too.
Okay.
I mean, there are some interesting details there with respect to one shot and few shot.
Oh, yes, yes, yes.
Yeah,
Okay.
and plus the other modalities like how they are uh, using the depth image and versus the like the audio like you alluded to, and how they are comparing it. So there
Hmm.
were some interesting details. Plus,
Yes.
there is code too. So he could have done a lot more here. So that's the comment
Okay.
that I have.
Sure. We'll keep it in mind and update this. Like maybe next time we can get a competitive start. Thank you.
Yeah, is there is like any doubts from other like any points which you need to make or something?
Or
Yeah,
anything in general, I guess, related to
yeah,
AI.
anything like any feedback or like anything mistakes which you found,
Yeah,
anything
yeah.
is
Mistake.
appreciable. So like I'll say my kind of thing. The thing is like you just gone into ImageBind like really directly without giving any intuition on multimodalities. I'm not being harsh here. I'm just saying.
Yeah, yeah. Thanks for that. So how would you
So
want me to introduce multimodality? Like just say that
like
then.
if you look
Mhm.
into M3 AE paper like which they mentioned before. I'll just go into multi MAE paper and every multi autoencoder paper. What they did is like they previously like no one like before that there was some kind of multimodality like let us say like clip or something, but on the audio space as well as in video space like there were really specific multimodalities, but on clip like you kind of expand it. So if you like go into like audio MAE something like that which they discussed before, that could give something like an an intuition and more like the purpose of this paper.
Got it. Got it.
Yeah, like I'm not a saint. Even I too make a lot of
Sure.
terrible mistakes
Sure.
when I'm presenting. I'm just saying.
No, no. No, no.
Yeah,
Thanks. Thanks
thank.
for the feedback. I was looking for that.
I'll just look into chats if there is any. And I think like that's it. So is there is like any questions, final questions related to it or feedback?
For the ones who didn't read the paper, were you able to at least get an idea of what they're trying to do?
Okay.
That's either a complete yes or a complete no.
So So like we still have 15 minutes left. Like even if you want to go to like nitty gritty details, you could also go, or like we could complete this session today.
I didn't make any slides pertaining to it, so I don't want to freehand it right now. I say something that I'm not perfect with.
Okay, let me look
Maybe I
into
can
my.
revise the slides as you said, and as you and Maya and Vaya gave feedback, and then maybe yeah, I'll post them in the Discord uh, channel with the nitty if that's fine.
Okay, speaking on this thing, like I have something in my hands right now. I'll go upon with Coca too, so that will also help in understanding. So I'll just share my screen for now. So yeah, this is like Coca, which was like introduced by Google. What they did is like same as this thing. These were like you could just say pre-image bind thing too. So what they did is like they used an encoder and they enable cross attention, just like in Clip. So the thing is like they kind of like got into state of the art results on classification on ImageNet. I think like that's still state of the art. I think last time uh, Dieter like came upon it, but still like as far as I knew, I could be old. The thing which I trying to emphasize on this or in representation learning is even if you like take out this decoder, you still have a really good encoder which could understand what you're doing. So that's the main purpose of this thing. That's the main purpose of representation learning thing. So this could like really help you on either of modalities. If you want to do in multimodality, yeah, you could just put it down, let it go. Or if you want to like work on single modality, you could just take it from it. So you could also see even like even if you look into like Video Poet or something, they'll just concatenate everything into one single algorithm. So that is also thing, but that's like totally outside of the topic. But the thing is like this is the thing which I wanted to say. So this Coco pre-training is like they kind of like made it into multimodal alignment with text decoder, same as like in Clip. But in Clip, what you do is like you kind of like classify it, and you just you have this name of and you'll classify it, and you'll take a dot product between these two alignments and take a maximum from it. That's how Clip works. For that, it like really worked well. So even now in Stable Diffusion and everything, you see Clip encoder, like Clip image encoder, or it will be some kind of based on Clip encoder. Like there is no denying in that. Even similar to that, we also see T5 encoders on uh, text to image models. So yeah, so to kind of like come upon with inspired by Clip, but Clip like does like really good job. Instead of captioning, like it will give you the attention not the attention metric. It will give you a matrix representation, and you could like take in samples from it, like what is near to it. So that's Clip one from Coca, what I suppose. So yeah. So these are all like the to-do reads after this paper. Coca as well as this thing, Blip. And with these two, like if you have a really intuitive understanding on representation learning, you could like learn upon with image to video and video to text. That's it. But still, what I really don't like on this papers, like I'm not the person to critique this, but really there is no other way to instead of using contrastive laws, some kind of distance based laws would be a really game changer at this point, because it won't be suddenly depend upon batch size. So all this contrastive laws and everything, the more batch size you have, the better. So that's why you get really state of the art results on pre-training on really large models with a really large batch size. So that's also a notable thing. So yeah. So you could just go upon completing this presentation, Srikar.
Yeah, so thanks for that, Marva. I will read those two papers as well. Uh,
Yeah,
and if you guys have any doubts, I guess I showed my email as well. You can mail me or you can ping me on Discord. Other than that, I have nothing to add. I'll take into my own consideration of adding in the few shot learning results being much better or almost giving at par performance with the specifically trained models. And even as you said, probably give them a brief history instead of directly jumping into it.
yeah,
Okay then,
do any,
thanks and take care, guys.
yeah, okay. Does anyone have doubt on my part, the Coca and Blip?
No, it was clear from my end. I'm just looking at the blog too. Google has also published a blog there. So yeah, I was looking at that
Yeah,
with
the
respect.
point which I was, yeah, sorry.
Yeah, with respect to the zero shot learning and the frozen encoders, you were clear in the point that you were trying to make. Thanks.
Yes, thank you very much. So let us all thank Srikar for his presentation. And thank you everyone for attending, making this session a success. Thank you everyone. Yeah.